All right, welcome everyone. Today, we're going to keep working with parametric curves and parametric equations. And specifically, we're going to see how we can eliminate the parameter to find, or to help us find, a Cartesian equation that really describes the parametric curve. So this is going to help us kind of picture what's going on with our parametric curve and parametric equations. All right, so let's just look at a few examples. And we're going to start with example 1. And this is the parametric curve and system of parametric equations that we looked at in the last lesson, that we started with in the last lesson. And what we're going to do is we're going to see how we can eliminate this parameter t, to find a Cartesian equation that really describes this parametric curve. And let's look at it. So what were our parametric equations? They're x equal to t squared minus 2t, y equal to t plus 1. And then we saw how to kind of graph this in the last lesson. Essentially just we went through some different t values, plotted the corresponding points, and then connected the dots. And we saw when we did this, we plotted a few points and we got a parabola. Now what we're going to do in this example is we're going to see how to essentially eliminate this parameter t and really try to find some direct relationship between x and y. All right, so now as it stands, these are kind of indirectly related to each other. X here is written as a function of time, y is a function of time. We're going to try to eliminate this time variable, try to combine these into one equation essentially. And really the way to kind of start with this is to look at your two equations and see if you can solve for t. And we can solve each of these equations for t. We can solve both of these. One is just a whole bunch easier. So this equation, we could do it. It's just going to take a bit more work. This equation is much easier to work with. So that's what we're going to do. We're going to start by solving this y equal to t plus 1 equation. We're going to solve it for t. And what do we get when we do that? Subtract 1 from both sides, and we get t is equal to y minus 1. Okay. Well, once we've solved for t, what we can do then is we can go back and plug it into this other equation. Wherever we see a t in this other equation, plug it in. So this is the first thing we're trying. Look at both of your parametric equations. Identify which one is going to be easier to solve for t. In this case, it was this y equal to t plus 1. Solve it for t, and then just take what we know about t now and plug it into this other equation. So when we do that, we get x is equal to y minus 1 squared minus 2 times y minus 1. If we wanted to, we could multiply all this out and simplify. And when we do that, we get y squared minus 2y plus 1 minus 2y plus 2. And if we keep simplifying, we end up with y squared minus 4y plus 3. And we can see here that that's what we expect from a parabola. Now it's x equal to y squared and some y terms here, so that's why it's tipped on its side. But it's a standard formula for a parabola. So that just kind of helps give us an idea of what this parametric curve is doing. And if we wanted to, we could kind of picture this parametric curve by plotting this Cartesian equation. So this is our Cartesian equation here, x in terms of y. All right, let's try another example. So this is really the idea here, is we're really just trying to get this Cartesian equation that really just describes this collection of points. And we're really trying to find just some relationship between x and y. Some direct relationship. All right, so let's do it again. This time for the parametric curve given by x equal to cosine t, y equal to sine t, where t is between 0 and 2 pi. All right, so for this eliminate the parameter, we saw last time, sometimes we can solve for t. That's the first thing we should think of. So eliminate the parameter, see if you can solve for t. Now, technically we could do that here, but then that's going to involve some inverse sine or cosine functions, and then we have to be careful of the t values when we use those. So that could pose some issues. But kind of taking a step back and thinking about what we're ultimately trying to do is we're trying to find, so with eliminate the parameter, with this technique, what we're really doing is we're trying to find some direct relationship between x and y. Right now, they're kind of just indirectly related to each other. All right, so that's what we want to do. And when we look at these two functions, they're trig functions. So you should kind of think of, when we see trig functions, we want to think back to our trig identities. So not always, but sometimes. It's sometimes helpful to think back to our trig identities, especially when we see these trig functions here. All right, so what is our kind of our go-to trig identity involving sine and cosine? Well, that's sine squared plus cosine squared is equal to 1. So if we think of that, sine squared theta plus cosine squared theta is equal to 1. All right. Well, sine squared, we have a sine term right here. Let's square it. What happens when we square this? We get a y squared. And sure. Okay. Cosine squared, well, x is cosine, so let's square cosine here, and that would give us an x squared. And it's saying this should be equal to 1. And this is our Cartesian equation. Now, it's probably a little nicer to write this as x squared plus y squared is equal to 1, but, fine. This is fine. And this is a recognizable equation. You've probably seen this one at some point before. This is a circle. This is a circle of radius 1 centered at the origin. So our Cartesian equation here is x squared plus y squared is equal to 1, which is a circle centered at the origin with radius 1. All right, so we already have kind of a good picture of what this parametric curve is going to do. It's just going to be a circle centered at the origin with radius 1. And we can check this, so we can plot a few points. So take some t values here and plot them, and find the corresponding points and plot those points. And what you would see is that with this interval of t, this time interval here, we're going to trace this curve out exactly one time. So we're going to go counterclockwise around the origin exactly one time. So we have this circle, and we know parametric curves have this kind of time component. So we think of it like a particle moving in the plane. And so what we're going to have here is, because our time interval is from 0 to 2 pi, and because our kind of our t value here, this it's almost like an angle measurement. This is something we've kind of seen with polar coordinates. We've worked with these types of parametric equations before, and this is what we saw with polar coordinates. And going from 0 to 2 pi, this was like our kind of our standard theta value in polar coordinates. And this was our conversion into polar coordinates, or into and out of polar coordinates, was x equal to r times cosine theta, y equal to r times sine theta. And here the r value is just 1 because we're dealing with a circle of radius 1. But this is kind of the standard conversion formulas that we used for polar coordinates. So really, polar coordinates is kind of a special case of these, or polar curves is kind of a special case of these parametric curves that we're looking at. So we have this x equal to cosine t, y equal to sine t, where t is between 0 and 2 pi. And if we wanted to, we could, plot out a few of the corresponding points on this curve. And what we would see is that because of these t values are between 0 and 2 pi, we're going to trace the curve out exactly one time. And that just has to do with kind of what we've seen before with polar coordinates, going around the origin counterclockwise for these sine and cosine functions. It takes us to go from 0 to 2 pi to get around the circle one time. Let's look at a related parametric curve. So let's, example 3, we have x equal to sine of 2t, y equal to cosine of 2t, where t is between 0 and 2 pi. We want to eliminate the parameter to find a Cartesian equation that describes this parametric curve. And again, we want to find a relationship between x and y. We see that we have trig functions here, sine and cosine, so we want to think back to our trig identity. Sine squared plus cosine squared is equal to 1. So let's try that here. So we're going to eliminate the parameter. So we're just getting rid of all the t's that we see, essentially, in these two equations. And we're going to combine them into one equation. All the t's should be gone. And now if we square x squared and we square y squared, what happens when we square x squared? Or what happens when we square x? We get sine squared times 2t. And what happens when we square y? We get cosine squared of 2t. Now these sine squared and cosine squared terms here, they have the same angle, 2t. So these angles are the same. And we know that when we have sine squared of some angle plus cosine squared of some angle, it's equal to 1. The angle just needs to be the same. So as long as these angles are the same, The sine squared plus cosine squared, we know it's equal to 1, and here we get our Cartesian curve. X squared plus y squared is equal to 1. So this is the exact same Cartesian curve that we saw, or Cartesian equation that we saw in example 2. So this parametric curve, different parametric equations, x equal to sine of 2t, y equal to cosine of 2t, where t is between 0 and 2 pi, it's still going to trace out the same curve, x squared plus y squared equal to 1. So it's still going to be a circle centered at the origin with radius 1. Now the difference here is we're going to have a different starting point. And because of this 2 here, we're actually going to go around the circle twice. So because of this 2, for our angle here, we're kind of doubling the angle. And what happens is that means we're going to go around the circle twice. So this is kind of the thing about parametric curves is, yeah, there's the kind of underlying Cartesian equation that describes the collection of points, but there's a lot more information that is kind of encapsulated with these parametric equations. So there's going to be different starting points, different ending points. There's going to be a direction that we kind of go around the circle here. And there's going to be kind of how many times we trace out the actual collection of points. So there's a lot more information with this parametric curve than with the Cartesian equation, but this just kind of, the Cartesian equation is helpful because it gives us kind of idea of what the curve looks like. But there's a lot more information here with this parametric equation. There's starting and stopping points. There's a direction that we travel along the curve. There's, how many times do we go through it? So there's a lot more information that we have here. But this kind of gives us what the underlying shape is, essentially. So that's what we've seen. We've seen in examples 2 and 3, 2 different parametric curves. These are very different. So we've looked at these 2 different systems of parametric equations and kind of talked a little bit about the, what the parametric curve is doing. And what we're seeing is that, yeah, we have these 2 different parametric curves, but the Cartesian curve is actually the same for each of these. They each gave us this x squared plus y squared is equal to 1. So these are very different parametric curves. In the first one, what would our starting point be? For instance, plug t equals 0 into these equations. What would our starting point be? Well, cosine of 0 is 1. Sine of 0 is 0. So our starting point in this case would be 1, 0. What would our starting point be here? So we're starting along the x-axis here. In this one, our starting point would be 0, 1. So we'd be starting on the positive y-axis. So just that little detail here, these are already different parametric curves. but ultimately they end up tracing out the same collection of points. So we really want to think of our Cartesian curve as just describing a collection of points. And then our parametric curves really give us kind of a lot more information. So they still describe the collection of points, but with extra information. So we might have our initial and our starting and ending points, our initial and terminal points. So our starting point here, we looked at it by seeing when t was 0, what was our kind of our starting point. Could looked at our ending point, our terminal point for 2 pi. There's a direction. So there's what direction as t increases do we go around the curve. So this was for increasing t. How many times do we kind of trace out the collection of points? And really there's almost a speed here. How fast do we go around the points? So in this parametric curve, we're tracing out that same Cartesian equation, x squared plus y squared equal 1, but we're doing it twice in the same amount of time. So if we were watching a particle go around the circle here, the particle in the second one here would be going much faster than the particle traveling in this first example we looked at. So there's almost like a speed. How fast are we traveling around our curve that's associated with our parametric curves? So these parametric curves are pretty interesting. They give us a lot more information here. And a lot of it has to do with, if we think of it as a particle moving in the plane, where do we start? Where do we stop? What direction do we travel in along the curve? How many times do we go back and forth? How many times do we trace out the curve? And almost like a speed, how fast do we trace out the curve? All right. Let's try another example. Just going through and given a parametric curve or parametric equations here, how can we eliminate the parameter? So how can we eliminate t to find kind of the Cartesian equation that describes the underlying structure? And all right, so we see x is sine t here and y is equal to sine squared t. And we might think trig identity. So we have some trig functions here, but the usual trig identity doesn't kind of jump out here because it's sine squared is equal to cosine squared. So we have sines here. We have x's in terms of sine, and then y is in terms of sine. So what we could actually do is, since we have x in terms of sine and we have y in terms of sine, instead of solving for t, we could just solve for sine of t. So you're just trying to look for anything that shows up in both equations and see if you can solve for that thing and then replace it in the other equation. So there's a lot of different techniques and little strategies here for how to do this. So sometimes if we have trig functions, you're looking for trig identities. In the first example we did, we just solved directly for t. But sometimes you want to look and see if there's maybe something else you want to solve for. So the trig identity approach, maybe we could get it to work here, but it's nothing immediately obvious. We don't have a sine and a cosine. But we could probably get something to work. But if we look at this, we could also solve, instead of solving for t, maybe we solve for something a little bit different. And so we have a sine t here. We have 2 copies of sine t over here. So we're going to be able to do this. Especially if we think of this y equal to sine squared t as really sine of t squared. And so that's what we're going to do. We're going to get sine t is equal to x. So we're just solving this equation for that common component. We're going to plug it in over here. And what do we get when we do that? Well, we're going to get y is equal to x squared. And there we go. We have our Cartesian equation. Now, there's a little bit of trickiness here in that, yeah, y equals x squared is the Cartesian equation that kind of describes this parametric curve, or the collection of points, but it's too many points. This is describing too many points. So if we think over to our x equation here, not every point and this is a parabola, y equal to x squared. Not every point on this parabola is actually a point on our parametric curve. So why is that? Well, let's look at what x is. X is equal to sine of t. And we know that sine of t, it doesn't take on every possible value. Sine of t, the sine values always fall greater than or equal to -1, but less than or equal to +1. So the sine function is always in between -1 and +1. And so what that means is, we solved our equation for sine of t here and used that to help us eliminate the parameter. Well, now there's this kind of restriction on that term. So we solved for sine of t, but there's some kind of restriction on, what the output of that function is. It only falls in between -1 and +1. So that means x can only be between -1 and +1. So, yeah, our Cartesian equation here is going to be y equal to x squared, but there's this extra restriction on it. And this just comes from the fact that we solved for sine of t, and we saw it was equal to x, and that puts some restriction on what the potential x values are going to be. So it's going to be for x between -1 and +1. So yeah, it is going to be a section of the parabola y equals x squared with this restriction on the x values. So between -1 and +1. So if we were to graph this parametric curve, it's going to be a section of the parabola. So we want to draw the section of the parabola y equal to x squared for x between -1 and +1. So here we've graphed kind of the whole parabola. This is the whole parabola y equal to x squared. We only want the section of it where x is between -1 and +1. So this is our parametric curve right here. There's kind of the underlying structure of y equals x squared, but then we saw that there was this extra restriction on x, where x had to be between -1 and +1. Now, if we wanted to, we could get an idea of how this parametric curve kind of traces out, or kind of how does our particle move along this curve. So just try different t values. So, we could start with t equals 1, or t equals 0 rather. And if at t equals 0, we would be at the origin. Then at t equals pi/4, we'd be here. And then at t equal pi/2, we'd be up here. So starting with t equals 0 and working our way up, we'd be going in this direction. So our particle, if we think of a particle that's moving, it's going to, at t equals 0, it's starting at the origin, and then it works its way up here. And then what happens after pi/2? Well, it starts coming back down. So then it starts coming back down, and then at t equals 3 pi/4, we're back to here. And then at t equal to pi, we're back at the origin. We're back to this point here. And then what happens after pi? So then we have what? T equals 5 pi/4. Kind of go up this section here. Now we're going up on the other side of the parabola. And then we get to t equals 3 pi/2. And we're up to this point. And then the particle just moves back down from there. So then we get back to 7 pi/4. We're back at this point right here. And then at 2 pi, we're back to the origin. And then there's no restriction here on t, so this just keeps repeating. So we have this particle that's just kind of oscillating back and forth along this parabola. So yeah, there's the geometry of the parabola here, that the collection of points that we're tracing out. But there's also a lot more information here. We're kind of going back and forth. We have this particle that's just tracing this parabola back and forth over and over again. All right, so that's why this technique is kind of helpful. We can kind of use this to help picture what the underlying structure is, and then plot a few points to kind of confirm the direction. How are we actually tracing out the points? All right. So one last little thing to talk about here, and that's just a few common parametric curves that we see from time to time. And if you go into Calc 3, these are going to be ones that you see quite a bit. So the first one is the system of equations for a circle centered at the point h, k with radius r. And you can kind of see what's going on here. So we have our r times cosine t. So this is just giving us, and then we have an r times sine of t. So that's just giving us the circle of radius r. And then we're adding h to the x component. We're adding k to the y component. And that just shifts the center point. And then kind of our angle here goes between the usual 0 to 2 pi, because that's what the period is for cosine and sine. So we get this circle that's traced out exactly one time where it's the circle centered at this point h comma k with radius r. So this is a fairly common parameterization for the circle. Now there's other ways to do this. As we've seen, for these curves, a lot of times there's different parameterizations that we can use, parametric equations that we can use, that ultimately give us the same Cartesian equation. So our Cartesian equation here for this one is x minus h squared plus y minus k squared is equal to r squared. So this is the Cartesian equation for a circle centered at the point h comma k with radius r. Now, what about the line segment? So, well, let's actually back up. What does this circle look like? So, might have our center point here, h comma k. And then what we're doing is we're drawing a circle centered around that point with radius r. And where it starts is it's going to start kind of parallel to the x-axis there. Kind of, if you imagine thinking back to polar coordinates, think of this as now the origin, and we're looking at the polar axis extending out from there. And then we're just going to go counterclockwise. And let me make this a little smaller. And we're going to go counterclockwise from there. So we get this circle of radius r. Now, that's one of the common shapes that we want to parameterize. So this is a common parametric representation for the circle. Now, we also want to work with line segments a lot of times. So kind of a common parameterization for a line segment is x equal to x0 plus t times x1 minus x0, and y is equal to y0 plus t times y1 minus y0, where t goes between 0 and 1. And so what this does is this gives us a line segment connecting points x0 comma y0 and x1 comma y1. So this gives us the line segment connecting these 2 points, where we start at x0 comma y0 and we end up at x1 comma y1. So there's a direction here for these parametric curves, as we've seen. So what does this look like? So we have 2 points, x0 comma y0. Maybe we have another point, x1 comma y1. And we're just looking at the line segment connecting those 2 points. And so this curve here, perfectly good curve in the xy plane, we can describe it with these parametric equations. And the direction here, it's important to remember our direction. This is our starting point, this is our ending point, and so we just kind of go along this line segment. We go in this direction. Now for our circle, we're going counterclockwise. So we start at this point and then we go in a counterclockwise direction around the circle. So what is the Cartesian equation for this line segment? Well, you can kind of go through and you can really solve either of these equations for t. So that'll be something, a good little practice to do. try to solve either of these equations for t. And what you'll get is, y equals mx. You'll get the slope. You'll see the slope formula in there. So you should get essentially you should get the point slope formula for the equation of a line. So you'll actually see when you do this, you'll see the slope formula. All right, so these are just two common parametric curves. Like I said, if you go into Calc 3, you're going to see both of these quite a bit. This is going to be something we want to do. If we have a circle, we want to be able to parameterize it, find the parametric equations. If we have a line segment, we want to be able to parameterize it, find the parametric equations. And so, we want to have this kind of keep in mind this relationship of going back and forth between kind of the Cartesian equation, which really just describes the underlying collection of points, but then also this parametric equation, or parametric equations, which kind of describe the direction, starting and ending points. How do we trace that collection of points out? And these are just two common examples that we see. All right, so let's stop there. Next time, what we're going to see is with these parametric curves and equations, we're going to see how to calculate our derivative, dy dx. How do we find the derivative of y in terms of x when we're given these parametric equations? That's what we're going to look at next time. So we'll see you then. Bye-bye.